Hello, everyone. I thought I'd work an example today. I'll just babble over the text as you all take an opportunity to read it. I want to remind you I have office hours every day from 2 until 4, every day except Friday. Okay. So the first thing we do is get a pen that works. First thing we do is the parsing step, where we take the information that's in the problem and we do something useful with it. So I have a ring, and the ring has a ring mass equal to 1.8 kilograms. Its radius is 0.58 meters, and I've got three masses that are 0.2 kilograms each, located equally around the ring. But we have to be a little careful, because when I place these masses, let's use the green for them. I have one here, one over here, kind of one over here. We're told that one of those masses is our axis. So this gets a little complicated, because we know that, and by we know that, I mean we've looked it up on a table someplace, that the moment of inertia of a ring in its middle, its center of mass, is given by mr squared for the ring. So we know that definition. What we don't know is the moment of inertia of the ring about its edge. All right. And that leads us to our approach, which is, let's find I for the center of mass, and then parallel Axis theorem to move it to the edge. So we do our approaches, and the first is we need I center of mass of this system. So this isn't necessarily hard. As long as everything's rotating about the same axis with it, which it is, I can use I about the center of mass of the system. It's just going to equal the I of the ring plus I of mass 1 plus I mass 2 plus I mass 3. So we looked up the mass of the ring already. It was the mass of the ring, the radius squared. Each individual mass coming from the center of the ring is located on the ring and just adds its own self to it. Let me get this written out, and that's because I is just defined as the sum of all the masses r squared so as long as you know the axis, which was the center of mass of the ring, we can just add these 3 additional masses to it. So the I center of mass of our system is just going to be big M, mass of the ring, plus 3 little m, masses of each of the nodules on it, and they're all at r squared. Okay. Having done that, let me do approach 1. Our next test is approach 2. Where we said that we would need to get the I of the rotation of the ring plus its masses at the edge. And we said we were going to do this with the parallel axis theorem. So that just means I need an equal sign, not a plus sign. And maybe back to black. And we got I of our center of mass plus md squared, where you'll recall that that's getting pretty close to a troll face. That if I know the center of mass is located here, but my, getting my symbols mixed up, sorry about that. So that would be our center of mass. And if we then constrain it to rotate around a particular axis of rotation, then this is the distance d. As we shift the mass to the edge. So for us, we're going to see something very similar, where the I around the edge is just going to equal the I center of mass we solved for the system, m plus 3m, r squared, and then we add the fact that we're moving the entire mass, m plus 3m, to the edge of the ring, which is just another r squared. So rotating this around the edge of the ring gives us 2m plus 3m r squared. We do a quick check for sufficiency, which is I'm on the edge. I know all of those values. We are ready to take the next step in our problem solving. Let's do a quick evaluate. We can evaluate our solution by plugging in numbers. Since we really have one equation that we've been working forward, let's set this to I at the edge to 1.8 kilograms plus 3 times 0.2 kilograms, and our radius, which I forget, the radius of the ring is 0.58. So 0.58 meters squared. Grab the calculator, plug numbers in. 2 times 0.58 squared times parenthesis 1.8 plus 0.6 and I'm getting 1.61 kilograms meters squared. So when we review our answer, this is difficult to do numerically. There's not necessarily a lot of experience in terms of just how big moments of inertia are. So part of what you can do to try to figure out if the review makes sense is just find the I center of mass of the ring itself. And that's just going to be the 1.8 kilograms, 0.58 meters squared. Keep in mind that it's easy to rotate a ring about its center of mass. So we would expect this value to be lower than the value we found. And I get 0.60. And again, kilograms meters per second. Sorry, that was a slip. Kilograms per times meters squared. Oh, and our units for I, we are expecting that to be what the formula gives us, which is just up here in the beginning. The formula gives us mr squared. So when we go down to the units, we are expecting this to be mass, kilograms, and distance squared. But let's take our most complicated version when we had kilograms plus kilograms, and multiplied all of that by meters squared. So we're going to see that we have for our units to be kilograms meters squared as expected. In fact, as a general review, all moments of inertia are going to look like mass times some distance squared. So if you're working a problem and let's say that you forgot to carry that too, the next line down would look a little vacant, meaning it would just be kilogram meter. Okay, so we reviewed it. We have a sense that it was significantly larger than the ring itself. So I think we can chalk this problem up as done.